Title of my talk this morning is Drizzle, Showers or Storms, How's the Weather Tonight? And you can see that there's a question mark. So how is the weather tonight? Well, if you're going to stay for the star party tonight, there's good news, because this is the synoptic chart for today, and you can see that there's a low pressure off towards the west, but over the whole of the subcontinent there's rather stable weather, so the prospects are quite good for clear weather tonight. So the answer to the question, showers, storms, there are going to be no storms or showers tonight that we know of. Okay, but when we talk about that weather that you've seen on that synoptic chart, all of that weather takes place basically in a layer which we call the troposphere, which extends up to around about an altitude of about 15 kilometers. So we live in that area. This is supposed to be Mount Everest over here, which has an altitude of around about 9 kilometers. So that's even within the troposphere, within the area that we experience all this weather. But what about above that? And you can see if you extend the atmosphere upwards, we have at least 4 layers above the troposphere. Above the troposphere we have the stratosphere going up to around about 50 kilometers. We then have the mesosphere going up to 85 kilometers. And then above the mesosphere we have the thermosphere, which goes from around about 85 kilometers up to 500 kilometers. And then above the thermosphere we have a layer called the exosphere, and that extends up to around about 10,000 kilometers. And that's the point at where basically you cannot recognize the atmosphere anymore. So we've got our own weather here, but there is another weather system which is going on in this area here, roughly between the altitude of around about 80 kilometers and 120 kilometers, and that's the area where the shooting stars burn up, which we call meteors, and these often come in showers. So if you go out and sit under the sky on any dark night, you're sure to see maybe 1 or 2 of these shooting stars. That's an example there. And this basically, these are sporadic objects, and we might call these objects then meteor drizzle. At certain parts of the year, if you're lucky, you will experience what's called a meteor shower, and then you might see 20 or 30 of these objects coming from a certain part in space. You will know that there is a shower in progress, because if you trace these paths backwards, they all seem to come from the same part of the sky, and that's what we call the radiant of the meteor shower. On very rare occasions, you might experience what we call a meteor storm. And this is a woodcut of the meteor storm in 1833, which resulted from the apparition of the Leonid meteors. Why do we have a woodcut and not a photograph? Well, simply because this particular storm was before the age of photography. So there are no photographs which exist of this particular meteor storm. But basically, meteors on this particular night fell at the rate of around about 10 to 20,000 meteors per hour. So this is really a meteor storm. The other thing about this, it's a woodcut, not a photograph. And of course, this happened before the age of the internet. In those days, they had the carrier pigeon. If only life was so simple. Okay, so on this particular evening, stars were reportedly to have fell like rain. We know, however, that they are not stars. So what are they? And the answer comes from this. This is one of the oldest remnants from the formation of the solar system. It's a comet. And what you see here basically is the 2 comet tails. So the nucleus is over here, and this comet was called Hale-Bopp. It was a comet which was very bright in early 1998. And what you see here basically is the 2 tails coming off of the comet's nucleus. This is the gas tail, or the ion tail, which is formed from the volatile matter in the comet, and this particular color you get from the ionization of carbon monoxide in the comet. And then you have this very bright tail here, which is the dust tail of the comet. and this shines by reflecting sunlight. It doesn't give off any light of its own, it actually reflects sunlight. So we have a dust tail and a gas tail, and that gives us clues that comets basically are made up of these frozen ices mixed in with dust. And this description was what led the astronomer Fred Whipple to call these objects dirty snowballs. Okay, so looking a little bit more detail about these comets, first of all, in terms of the volatile matter, we find that this particular comet, Hale-Bopp, was analysed in detail, and for the most part you can see that it's made up of water vapour, carbon monoxide and carbon dioxide. These are always the three most prevalent gases in any comet. So for 100 parts of water, you can see that there's 23 parts of carbon monoxide and 6 parts of carbon dioxide. We also see smaller amounts of various other chemical compounds, so oxygen compounds, sulfur compounds, nitrogen compounds, and hydrocarbons. So once again, if we look at the detailed analysis of all the different species which were found in this comet, you can see that there's a wide range of different chemical species which, when they're far from the sun, they are basically frozen, and these all comprise the ices in the comet. So once again, you can see water, carbon monoxide and carbon dioxide. You can see simple hydrocarbons like methane, acetylene, ethane. There is some formaldehyde, always formed in comets. And on Earth, we can polymerize formaldehyde to get a simple plastic called polyoxymethylene, which is sold under the trade name of acetyl. And there is actually polyoxymethylene in comets as well. So they have actually detected that there is plastic in comets. So it's not only that we've got plastic in our oceans, which we put there by the way, there's also plastic in comets. Some other interesting molecules in comets. First of all, we have hydrogen sulfide, which the school children here will know as the rotten egg gas in the stink bombs. I'm sure you've made that in the past, if you were naughty like me. So it's hydrogen sulfide, so a comet is a smelly place. We also find things like glycine, which is an amino acid, which is a very important building block in the formation of life. And then we also find things like hydrogen cyanide, which is one of the most toxic substances known to man. So hydrogen cyanide and hydrogen isocyanate. In actual fact, hydrogen cyanide was detected in comets already late in the 1800s. And so when Halley's Comet came around in 1910, and it was realized that the Earth would pass through the tail of the comet Halley, there were some astronomers who predicted that there would be dire consequences as a result of that. And so one report, for example, said, warning to the inhabitants of the city, and this I think was in New York, close your windows and keep indoors, for the Earth will soon pass through the tail of the terrible comet, and its poisonous gases will fill the heavens. On the other hand, there were some unscrupulous individuals who made money out of this by selling what they called comet pills, which were supposed to ward off the effects of the gases and the dust in Halley's Comet. So Halley's Comet came and it went. It left behind its gas. A lot of people got rich out of it, and as far as we know, nobody actually died as a result of passing through the tail of Halley's Comet. Okay, so this is a comet nucleus. This is what it looks like when it's far from the sun. This is the comet Churyumov-Gerasimenko, discovered by 2 Russian astronomers. And you can see this is a picture taken from the Rosetta spacecraft. And you can see this is basically dust, and it's held together with these ices. And so when it's far from the sun, it's a solid object like this. This goes around the sun once every 6.5 years, and so once every 6.5 years, the surface becomes depleted, and you can see these areas where material has melted and swoon away as it goes around the sun. Okay, that's another picture of the same comet while it's far from the sun, and by now the spacecraft was already in orbit around this particular nucleus, waiting for it to switch on. And so what happens is, as the comet in its orbit, and as I said, it goes around the sun once every 6.5 years. So in deep space, the gases are frozen. As it approaches the sun, and crosses the Earth's orbit here, it starts to come under the influence of sunlight, which warms the comet. It melts these ices, and then what happens is you get this. So that is the same comet which is now switched on. We now have these jets of gas and dust which are being emitted, and so what's happening here is it's now releasing these dust grains into the orbit behind the comet, and it's these dust grains, and if we pass through those, you will see as meteors. So what are these dust grains? So the composition of cometary dust, basically it is mainly things like silicates of the elements calcium, magnesium and iron, two minerals particularly called olivine and pyroxene. This is olivine and this is pyroxene, and so these are typically the types of minerals that you find in comets. We also find some more exotic things which we call gems, which are just glass embedded with minerals and sulfides. We call those gems. And then there's a complex organic solid material called chong, which is a mixture of various compounds of carbon, hydrogen, oxygen and nitrogen. We've managed to collect these particles. So this is, for example, a sample from a high altitude aircraft which flies at a very high altitude above the Earth. It deposits, or it basically when it's in flight, it puts out a little paddle. And on that paddle there is a sticky material called aerogel. And as it sweeps up these particles, they get embedded within the aerogel. And then these can be brought back to Earth and analyzed and put under a scanning electron microscope, which is exactly what happens here. So this is a cometary particle, piece of a comet. Which one we don't know, but so it was in orbit around the Earth. And you can see it's a massive aggregate of other smaller particles. And this is typically the size of the particle that you will see when you see a shooting star. And to give you some idea of how big that is, there is a bar there, and that bar there is 1 micron in width. So 1 micron is there. The width of a human hair, by comparison, is somewhere between 18 and 180 microns. So depending on your age, whether you're fair, you've got fair hair, you've got dark hair, the diameter of your hair will be something from around about 18 to 180 microns. So the smallest, fair hair people like me, when I had hair anyway, my hair was about 18 microns across. So this particle is smaller than the diameter of the hairs on my head. And that is typically what you see when a meteor comes into the atmosphere. So this is a comet which went around in 2007, early 2007. It's Comet McNaught. And you can see that these comets, as they go around the sun, they have the capacity to spray vast amounts of dust into their orbits behind them. This is a picture which was taken by amateur astronomer Simon Walsh. We went down to Paris in the Free State, so he took this picture. The comet is here, and what you see here is individual streamers of material as this comet was ejecting matter into space over time. So this is a period of around about 1 day. This is 2 days, this is 3 days. So there's about 4 or 5 days of dust in that tail there which has been sprayed by the comet. So this is over a very, very vast area. So if you were the Earth now passing through this debris stream, we would get a very nice meteor shower. As we pass through each of these individual filaments, you would see the rate of meteors go up and then come down, go up and come down. Unfortunately, this particular comet, we don't encounter its orbit, so we don't get a meteor shower from this particular comet. But one comet that we do is Comet Halley. This is a picture of Comet Halley's nucleus, which was taken from the Giotto spacecraft in 1986, and you can see these jets of material which are spraying dust into its path. So here you have the orbit of the comet around the Sun, intersecting with the orbit of the Earth. First of all, in early May, the first week of May, we intersect the orbit of Halley's comet and we get what's called the Eta Aquarian meteor shower. A few months later, we cross that orbit again in late October, and then we get what's called the Orionid meteor shower. So Halley is one of the few comets which actually we cross its orbit twice in a year. Most comets we only get one shower per year. The question is, if these are meteors from Comet Halley, why are they not called the Halleyids? Why are they called the Etoquariids, or are they called the Orionids? And the answer is to be found in this slide here. So this is typically what you would see if you were sitting outside in early May, just before dawn, and looking towards the east. We have the constellation over here of Aquarius. Over here is Cygnus the Swan, and I can't quite see it from here, but anyway. So what we have here is I've represented 4 meteors by these arrows. What happens now is if we trace the path of these meteors backwards, there's a point at which they intersect. So if we take that away and represent that, that is the radiant of the Etoquariids, and it just so happens that it comes very close to the star Eta Aquarii. So these meteor showers are basically named not after the comet which spawned them, but after the constellation from which they emanate. So this is the Eta Aquariids, and they come from very close to the star Eta Aquarii. There are a few meteor showers which we see each year. So we see, for example, the Eta Aquariids we've just mentioned. They give us a shower in the first week of May. The Perseids in August. We get quite a nice shower every year from those. Also from the Orionids, which is coming up in October. The Taurids, they give us rather a drizzle than a shower, and every now and again, roughly every 12 years, they give us quite a nice shower. The Leonids, currently they are drizzle levels, and every 33 years we get a storm from the Leonids. That happened last in 1999. 2000 thereabouts, so in 2032 we can expect once again storm levels of the Leonids. And then our strongest meteor shower of the year is the Geminids. They happen, they're at their peak on the morning of December 13 and 14. They give us a strong shower each year, and that appears to be getting stronger and stronger every year as well. So that's 1, 2, 3, 4, 5, 6 or 7 showers there. In actual fact, though, there are far more than that. We have in the working list of the International Astronomical Union currently 790 different meteor showers, many of them waiting to be confirmed. So this is basically a plot of all of the meteor radiants that exist, basically in the northern hemisphere and on the equator. So the equator is here, and every single dot that you see there is the orbit which has been determined for a meteor coming into the atmosphere. And that's been done basically by taking images of these meteors with 2 cameras separated by a few kilometers apart, and then we can triangulate the positions and work out the orbits, and that gives us these particular radiants. So this is the path of the plane of the ecliptic. So there are a lot of showers in the plane of the ecliptic, but you can also see there are a lot of meteor showers which come from the Oort cloud, which are in the northern hemisphere. So does that mean that there's nothing in the southern hemisphere? Because we see here there's no radiance down here in the southern hemisphere. The answer to that is no. It's just that at this stage all of these cameras are in the northern hemisphere. Nobody's been doing this type of work in the southern hemisphere, and that's what we're busy remedying at the moment. So we are at the moment putting in a series of, or network of cameras at 2 stations. There will be 16 cameras, and we're going to start to map these meteor radiants from the southern hemisphere as well. So that's typically the output from these cameras. These are all images of meteors or shooting stars which have been taken from these cameras. You can see that there are stars on all of these frames as well. And because we know the positions of these cameras, and also we know accurately the positions of the stars, we can work out exactly what the trajectories are of these meteors, and that enables us to then determine the orbit of the meteor on the image. And hopefully in the next few months, when this network in South Africa comes online, we're going to start to fill in the gaps of all the meteor showers, and we will have then basically a complete coverage or a complete synoptic map of the heavens and where these meteor showers occur. So to come back to this one, that's the weather for today. You get these synoptic charts maybe 3 or 4 days in advance. After that, it becomes rather difficult to predict what the weather on the lower atmosphere is going to do. If we look at the situation with the upper atmosphere, with these meteor showers, this is typically what we can expect, and we can predict these very accurately. In fact, we have, for example, with the Eta Aquariids, we have actually backtracked and we know exactly when these particles left the comet with an accuracy of around about half an hour compared to when they were released from the comet maybe thousands and thousands of years ago. So we can predict these meteor showers with great accuracy. So the ones that are coming up for the rest of this year, first of all, we have in late October the Orionids. They form quite a nice shower, once again the remnants of Comet Halley. Unfortunately, the date of their maximum on the 22nd of October, it's very close to the full moon on the 24th. They will be followed then in November by the weak activity from the Taurids, the southern Taurids, the northern Taurids, and then the Leonids. The Leonids now back down to their drizzle levels, and they will then come back to storm levels in the next 30 years or so. There is a potential for a storm activity this year from the Alpha Monoceratids. This is a shower which has only been observed 4 times in the past, in 1925 and 35, and then again in 1985, 1995, and there is a potential that once again this may undergo a storm this year. Again, unfortunately, it corresponds with the time of full moon, but obviously with such an important event, we will definitely be watching to see if anything happens. Then we come to December. There are a number of minor showers here, but we then have the Geminids, which is our most reliable meteor shower. It's getting stronger and stronger each year. If you observe the shower on the morning of December 13 and 14, you are pretty certain to see 60 or 70 meteors in an hour. You can see that its rise is more slow to the maximum, and then after maximum it drops off very, very quickly. So that is a real effect, it's not an artifact. So by all means go out and have a look at these showers. You really need to get yourself under a dark sky, otherwise you will only pick up the you won't pick up the fainter meteors. So that is a dark sky. If you're observing under conditions like that, where you have washed out all of the Milky Way and these fainter stars, you will also wash out the fainter meteors, and therefore you will only see the brighter objects. And that's typically what we are doing. So this problem of light pollution is becoming a great one, particularly for us meteor astronomers. And you can see here the different urban centres where the problems are. This is so on the Witwatersrand here in Gauteng. You can see my neighbour's floodlights there too. I've tried to get him to put them off, but he won't. Unfortunately, as a result of that, the only place where it's worse is here on the banks of the Nile. You can also see here that the number of spaces in South Africa where we really have dark skies is starting to diminish. So we really need to all take responsibility and do something about this. So if you want to watch meteors, and I do watch meteors quite successfully here from Kempton Park, so I'm sort of on the edge of this area where it starts to get particularly bad. If you're here towards the centre of Joburg, you've got no chance. So if you really want to see meteors, get yourself outside to one of these areas, and you can start to look these maps up. These light pollution maps are available online. So if you want to know if you're in a good area to look at meteors, you can find your location on these maps, and this will tell you exactly what the light pollution levels are around you. Okay, so that's basically it. So I've said to you that the weather for today, there's going to be no showers up to an altitude of around about 10 or 15 kilometers. But remember, that's not the only weather that's on the go. There's always this weather in the form of shooting stars as well. Thank you very much.
thank you very much, Tim. It's most interesting. Are there any questions? Yes, sir.
Yeah. That one where you show 760 meteors that have been tabulated in other places, I see they're different colours. Is that the actual colours of the meteors as well?
No. No, those colours are just for effect, so that you can separate. So you can then see every colour there will belong to a specific shower. So the Geminids, for example, will all be orange, and it's just to show that they are Geminids and differentiate the different showers.
Any others? Yes.
With that meteor storm, you can see the building, the house buildings. Would they have been visible, or is it sort of a composite picture? Is it that bright that it would light up buildings?
The one with the Leonids.
Woodcut.
The woodcut.
Yeah.
Yes, the chances are they would have, because we had a storm from that shower again starting in 1998, 1999. So it comes every 33 years. So it was 1833, 66, 99, 1932, 1966 there was a storm, and the next one was predicted in 1999. And the year before that, in 98, we were taken by surprise by what was called the Leonid fireball night, where all of these particles were very large particles, so they were very, very bright. And Venus, if you look at Venus, it has a magnitude of around about -4. Venus, on its own, can cast shadows under dark skies. So you had the situation where you had all of these meteors, these fireballs, and they were around about magnitude -8, -9. So each individual meteor was able to cast a shadow. Now with this meteor storm, you had 10,000 to 20,000 per hour. So it literally was enough to light up the landscape.
How widely was that spread? Northern hemisphere or southern hemisphere?
Anybody that was dark would have been able to see that, but it's a northern hemisphere shower, and so the best place to see it is in the northern hemisphere. In the southern hemisphere, the radiant only rises about 2 hours before dawn. So from here, we would have only seen that for the last 2 hours before dawn, and then it would have been too light.
Which guy made that woodcut? What country?
Not quite sure.
Austria, Norway?
I don't know.
That Hale-Bopp core, how big was that picture that you showed us?
Well, the nucleus of Comet Hale-Bopp was about 40 kilometers in. Yeah, but the tail is millions, millions of kilometers.
Any more questions? Yes, sir.
When these things burn up, what is the combustion product? What comes down to Earth?
Ash.
And how much per day?
10,000 tons.
No, we're putting on weight on a daily basis.
Actually, we're not. It's actually in balance. So we get hit by about 10,000 tons a day, and we lose about the same from volatile gases like oxygen, nitrogen, which actually is at the edge of the exosphere, and then those particles get carried out into space. So the mass of the Earth is actually pretty much constant.
Oh, good. Didn't know that. Thank you. Yes, sir.
Now and again, when I get up on top of my roof to go and paint it, it's full of stones. And I used to think it was my neighbours throwing rocks at dogs. But I think that it's actually coming from outer space, because there's a lot of very small ones. And some of them are magnetic. Are those actual meteors or what?
I doubt it. I very much doubt it. I think that's probably just stuff which gets from daily human activities, gets suspended and carried up, exactly that. So it gets carried up on the wind and then deposited on your roof. I doubt that's meteoritic.
Well, if there's no more questions, then I have a job to do as president of the ASSA. And at the AGM of the Astronaut Society of Southern Africa, Tim was awarded the Overbeek Medal. This is a medal which has recently been created in honor of Danny Overbeek, who was a renowned astronomer, observer in South Africa. And the medal is for the amateur member, the member of the ASSA, who's done a remarkable amount of observing of a high standards. So I'll read out his citation. Tim has been a long-standing member of the ASSA, having been awarded a Long Service Award in 2008 along with honorary membership in 2005 and a President's Award in 2006. His main interest is in comets, meteors and asteroids, and he has made significant contributions to our understanding of these objects through his meticulous observations and detailed recordings of a large number of these events. They have been published frequently in Manasseh, which is the Journal of the Astronomical Society, and other publications both nationally and internationally. His presentation at a recent SA symposium in 2018, where he described participation of the Camera for All-Sky Meteor Surveillance, which he talked about just now, network in conjunction with the City Institute, was one of the more significant papers at the symposium. CAMS aims to detect meteor streams from potentially hazardous comets, and this clearly demonstrates his capacity to develop an observing equipment and his ability to collaborate internationally. His recent outstanding efforts as a part of the team tracking down the bollard over Botswana has given the ASSA a prominent standing internationally of press briefing in Gaborone, Botswana, highlighting the details of this remarkable event to be published in Manasseh. I can think of no more deserving candidate than Donnie of the Overbeek Award than Tim Cooper. And we're very fortunate today that we've got Donnie Overbeek's daughter and son here tonight to make a presentation to Tim. So Tim, would you please come and collect the medal from Margaret? And well done, Tim. Much deserved.